In this episode, we're going to be simulating the mist above the wave crests. When waves roll, some water mist will appear above the wave crests. Meanwhile, influenced by the airflow, the water mist will diffuse, and the direction of the airflow is affected by the motion of the ocean surface. If the mist is a major highlight in the scene, you may need to put much effort for a perfect look. Considering the shot in our scene, a simple and fast way can totally do the job. Let's first import the tsunami into a new geo. As said just now, the mist mainly forms above the wave crests. So we extract the peaks of the ocean surface through the cusp attribute. Currently, the tsunami is oblique, which is a very troublesome thing for the adjustment of parameters. So I'm gonna rotate it to be straight and then bring it back after the mist simulation. Previously, we rotated it through this transform node. Simply create a reference copy of this transform node, make invert transformation independent, and check it. This way the tsunami returns to be straight with only the ocean spectrum animation. But the paths on the reference copy are relative paths rather than absolute paths, and they will be missing when we copy the reference copy into another geonode. So we need to create a reference copy manually. Drop a transform node over here, get the parameters linked, the needed ones only. Tick invert here. Good. The background part is nearly invisible, which can be skipped. Let's just focus on the mist in the foreground. There is a group which was created for subdividing the foreground tsunami. Let's obtain the foreground as per this group. Then we extract the peaks through the cusp attribute. Now the range is a bit too large. We need to scale it down. I'm going to keep the upper part and get rid of the lower part. So drop a box to box up the upper part of the tsunami. We can check it out in the camera view. Don't forget to add a transform node to get the correct position. We extract peaks in the selected area. Alright. Add a clean node to get rid of the unused polygons and all the attributes and groups. Besides, a high subdivision here is necessary, which can help us obtain an accurate source. What's more, a smaller source with some space in between is good, so that the distribution of the particles will be more random. Let's cache it out. Because this pop simulation is not easy to form a good look, we set the start frame to -50 for pre-simulation. Okay, done. Into the camera view to take a look. Perfect. We drop pop network. Get the start frame up top and the file cache linked. Okay. We scatter points on the surface and toggle off max points here. Set a proper quantity and a relatively short life because the mist disperses rapidly. Increase the life variance. Now the particles live for 1 second at most, that is 30 frames. Then drop down a pop force. Come up to the force here. The tsunami moves toward the negative x direction, so let's set the force on the x and y direction. Notice here, up the amplitude. Set a slightly bigger swirl size because the mist has few details. Like we said before, it should be proportional to the scene. Next, duplicate the pop force. Bring up swirl size to add some variations to the mist overall. Set a larger amplitude also, or the noise will take a little effect. And here, remove the force. Keeping one force is fine. Okay. Before caching, we clean up unused attributes and groups. Keep age and velocity only. Later, we'll set up the p-scale through the age attribute. Well, let's cache it out. We can see the mist becomes rather less from the middle of the flowbook. There is some mist at the beginning, but becomes less later. Because the tsunami rises high gradually and swallows most particles. Let's take a close look. Most particles are under the tsunami. There are a few approaches to handle it. Here I'm going to show you a common method first. Extrude the tsunami to form a volume. Uncheck flatten base. Give it a bit larger depth. Then convert it to VDB. Raise voxel size first to avoid computer crashing, and then lower it gradually. Try to let VDB perfectly match the original mesh for a more accurate collision. It's still slightly larger than the mesh. Shrink it inward. There we go. Cache the VDB out for a faster operation. Next, we import it into DOP. Drop a static object. Select volume sample, paste the path of the VDB over here, and tick Use Deforming Geometry. I won't add other collision objects. Well, the mist should collide with the buildings, but considering it takes up a small proportion of the camera view, even with the collision, it is almost invisible. What's more, the simulation will run pretty slow, which is not cost-effective. That's why I prefer no other collision objects. No matter what elements you may take the shot into consideration. Say it's not a close-up, then we can add the collision objects selectively. Briefly speaking, as long as the final effect is good, the more efficient the better. Besides, because the upward force is not big enough, the mist almost disappears in the middle. Even at the beginning, the mist is not high enough. Okay, drop in the pop-up. And multiply the force. Okay, let's solve it to see the difference. After modification, there is some mist in the later part. But there arises a new problem. As the force is increased, the mist is disturbed too much and looks kind of weird. We may have no clear idea of the real mist on a tsunami, yet the mist above the large waves is common. Basically, it goes straight without too much turbulence, because there's no airflow coming from various directions. Yeah, we will fix it later. Let's get back to the interaction issue for the moment. After adding the collision object, we can see there are no particles under the tsunami. Instead, they are on the surface now. Here, I'm going to show you another method to deal with it. The VDB is no longer needed in this case. Just let the particles return to the surface when they enter the tsunami. The tsunami VDB helps here. Drop a volume sample to sample the VDB. Now the depth of the tsunami surface is 0, and it gets smaller inward and larger outward. Okay, next, let's make the particles that enter the tsunami turn around. Drop a volume gradient to get the gradient of the VDB. Then we make a compare. When the particles enter the tsunami, that is, the depth is less than 0, we let them move outward and at their original position. For the particles outside the tsunami, just keep them where they are. Then output the result to position. Now the particles won't enter the tsunami. Okay, let's solve it to see how it goes. 50 frames are fine, because it's just for testing. Okay, done. Apparently it works. But the two results differ a bit. Let's take a close look. Some particles cannot match the tsunami well. Actually, all the gradient inside and outside the tsunami has outward. Besides, the particles are not given a correct distance. That's why some particles cannot match the tsunami well. Okay, let's first change the direction of the gradient. Simply add a negate node. Now the gradient turns inward. But we still need an outward direction for the inside gradient. So we can multiply it with the value sampled by volume sample. This way, the outside direction stays as it is, and the inside direction heads outward. Thus, those particles are given the correct direction and distance. Alright. Let's make a compare. Cool, it's fixed. Regarding these two methods, they end up pretty much the same. Here I apply the second one. Next, let's get down to the issue of the particles being disturbed too much. Bring down the pulse length, because the larger the value, the faster the particles wiggle. Besides, we can see some particles form into lines. It's not a big deal. We can simply add a pop replicate node. Good. Besides, the particles are too diffuse. To create some details like tendrils, we drop down a pop interact. Position force controls how strongly particles force each other apart, which is not what we want. Increase the velocity force, which can force the particles within the set range to match each other's velocities. The larger it is, the faster they will match. That's why it helps particle clump. Besides, I'd like to take the multiplier up a bit. Okay. Let's cache it. After modification, the mist is higher than before. Then let's check out the dynamics. The turbulence of the mist is proper now. Cool. Display point to replicate. Remember to take copy source attributes so that the age attribute can be inherited. Next, we set up the p-scale based on the age attribute. To determine a good p-scale, we need to check out the converted VDB. For the sake of observation, we extract a small area out. Take velocity blur, which can blend the particles well to get a motion blur look. Then we adjust the curve. Select B-spline for a smooth transition. The left of the ramp stands for the mean value of the age, the right stands for the max. The mean value means the particles are just born. The max value means the particles are about to die. So let's scale it down to make them disappear naturally. And I prefer not to set it to 0 when particles are just born for a smooth transition. Then we scale down it overall, so the particles will be of a higher resolution. Too small p-scale may cause particles being invisible, but we can thicken the material later. In some cases, we don't have to increase p-scale to thicken particles. After all, the larger the p-scale, the fewer the details of simulation. Drop density in. That's it. Well, done with the conversion of particles. Let's convert it to volume. Then compress it. Lastly, link it to transform. Next, I'm going to render it. Import it to a new geo. The mist is pretty thin, much different from other simulations. So I'm going to create a new material. Render a few frames. All right. It looks good, just gets a bit invisible in the later part. We will thicken it when adjusting materials. So much for the mist simulation. Let's call it a day. See you soon.